Welcome in. The next session is titled MIPI Automotive SerDes Solutions, New Developments in A-PHY and the Mass Connectivity Framework. And with me today, we have three speakers. We'll have Ido Cohen, co-chair of the MIPI A-PHY Working Group and Director of Strategic Innovations at Valence. Raj Kumar Nagpal, co-chair of the MIPI A-PHY Working Group, chair of the PHY Steering Group, and chair of the DeFi Working Group, and senior manager at Synopsys. And speaking first, Ariel Lasry, Vice Chair for the MIPI A-PHY Working Group and Director of Technical Standards at Qualcomm. They'll be presenting, as I said, MIPI Automotive SerDes Solutions, New Developments in A-PHY and Mass Connectivity Framework. We will have a live Q&A at the end of the session, so please feel free to use the questions panel on the right-hand side of your screen, and we'll do our best to answer all the questions at the end of the session. So with that, please take it away.
Yeah, thank you, Justin, for the kind introduction. So I am Ariel Lasry, and I will present the first part of that. So I will start by giving an update on the MIPI Automotive SerDes Solution, also called MAS. This will be followed by Raj Kumar will talk about the A-PHY overview, and this will be followed by Ido, who will talk about next generation A-PHY before we will conclude and open the floor for Q&A. So let's start with the MIPI Automotive SerDes Solution, also called MAS. So what it is all about. So MAS is a framework for integrating sensor and display with functional safety and security. So to provide end-to-end functional safety and security protection directly from the sensor pixel data where they are generated down to the ECU where they are consumed, or from the ECU where the graphic processor is producing the image data for being displayed on the display module. And this solution is nice with MAS because this end-to-end protection works over A-PHY network with a long-reach A-PHY, and it works as well on native A-PHY solution where you may have A-PHY integrated into the sensor, or over a bridge solution, or over a mixture of bridge and native A-PHY. So there are three main elements to MAS. The first one is the extend. This is the extension of the mobile protocol by providing additional feature to enable end-to-end functional safety and security protection. So we have a number of specifications. For example, the camera service extension for CSI-2. We have the display service extension for display, and we have the CCISE, which is protecting the control channel over sidebind I2C. And we have the MIPI security specification, which is providing the framework that is used by camera and display service extension. The second part is the protocol. So we enable the reuse and leveraging of well-proven mobile protocols like CSI-2, DSI-2, but not only mobile protocol for MIPI, but we also enable the reuse of external standard protocol like VESA DisplayPort and other common interfaces such as Ethernet, I2C, GPIO. And for all of that, we provide A-PHY protocol adaptation layer to be able to reuse the existing protocol and take benefit of the evolution of this protocol while being extended for functional safety and security for automotive. And the third piece, last but not least, is the A-PHY, which is basically the foundation of the whole MAS, providing a PHY for a robust automotive link with excellent resilience and immunity to EMC noise. And Raj Kumar will provide more detail later in this presentation. Here we provide some example of supported topology for MAS. So there are two popular topology. For example, on the left side, you can see the camera and sensor aggregation, where each sensor has its own A-PHY link going to the ECU. And on the ECU, you may have an aggregator device. And the beauty is that we are able to provide end-to-end protection from the sensor to the ECU through the aggregator. Another popular topology is, for example, the daisy chaining of heterogeneous display. When I say heterogeneous display, I mean mixing MIPI display with DSI-2 and VESA display with DisplayPort, for example. So in that example, you can have a single graphic processor that output 3 streams over a single A-PHY cable going to the free display, and must provide the end-to-end protection from the ECU to each of the display stream on the chain. So this is the master stack diagram. This is there to represent all the specifications that are covered by the MIPI framework. At the bottom, you can see the A-PHY, which is the base foundation there with the PHY layer and the link layer. Then on top of that, we have 3 stacks. We have 1 stack for MIPI CSI-2 camera. We have 1 stack for MIPI display and another stack for VESA display. And each of these stacks is connected to the PHY by the protocol adaptation layer. And above the protocol adaptation layer, we have the original protocol. And above the original protocol, we have the service extension, which provides this additional end-to-end protection for safety and security. At this point, we released last year all the specification up to version 1.0 of the service extension. We provide all the functional safety feature, and now we are working to complete the security feature to be released by next year. And along with the protocol, we also have all the supported interfaces, so that it's often that along with a CSI-2 stream, you also want to tunnel I2C stream, or along with DSI stream, you may want to tunnel also Ethernet stream. So we are able to do all of that over a single cable. So this is the status of the specification. I'm not going into the detail of all the spec. The slides are available afterwards, so you will be able to check in detail. Let me go into the detail of what is done for camera. For example, in the camera service extension, CSE 1.0 has been already released last year. It already provides all the what we need for end-to-end functional safety services. It is using message-based functional safety protection. Each packet is extended with a so-called SEP packet, a service extension packet. Then we add a CRC and message counter for the protection. It also features some test pattern generation and error injection in order to check whether the system is able to detect error when error occurs. So this is very important for diagnosis. And it has the ESS-ECI protocol to enable end-to-end protection of the control plane, which is running over the sideband I2C channel. And now we are working on CSE 2.0 to be released next year, where we will have the main feature is to add end-to-end security services with encryption and authentication. And Phil and Rick will explain later today about that. We have a new protocol, which is the FSED, that provides frame-based protection, as opposed to the SEP in CSE 1.0 that provides only a message-based protection. I will come to that in the next slide. And we have the CCI-SE version 1.0. This is something new. This is what we have done is that we have taken the ESS-CCI spec from CSE 1.0 and put it in a separate document, which is called CCI-SE 1.0. Because this is a general protocol that can be used to any device that is using I2C. And since we want to protect it end-to-end, also for other devices than camera, this has been put in a different spec. So this CCI-SE is fully backward compatible to what is already existing in CSE 1.0, and it provides additional protection of the control plane also for security services, not only for functional safety. Yeah. So, that I jumped 2 slides at one time. So, yeah. So this is an example of the 2 protocols, SEP and FSED, with camera service extension. I know it looks a bit busy, but let me walk you through. On the left side, you can see the CSI-2 image frame and the packet before any protection is applied to the frame. In the middle, you see all these packets are taking the payload of the CSI-2 packet and extending that with SEP header and SEP footer, where we put the functional safety and security tag elements like a message counter, CRC, MAC. And this is happening on a message per message base or packet per packet base. And on the right side, you see the FSED protocol, which is applied to CSI-2, where we use exactly the same CSI-2 packet as we had before, but we add this orange message that you see here just after the frame start and the orange message after the frame end to transport the MAC and CRC for the functional safety and security protection on frame base, as opposed to in the middle where it is on message based. The same method or similar method we applied also for display service extension with DSE. You can see this is an example of DSI-2 video frame, and this little orange FSED, this is where the FSED message is happening in the video frame, and it transport all the required CRC and MAC that are required for protecting the active area as well as the transport stream of the display service extension. So what we add in addition to the DSE 1.0 is that we're also able to protect each region of interest individually in order to increase the diagnosis coverage. I will go quickly through this one. We have also additional functional safety support for compression. This is necessary because when using compression, if the compression is helping to have lower bandwidth on the same wire to be able to address a higher resolution display. But if you are protecting after compression engine, this is not a really end-to-end solution. So what we are doing is that we are including the compression engine into the protection, and we are calculating the CRC over the reconstructed pixel data on the transmitter side, as well as on the receiver side. And for that, and by that, we get the end-to-end protection, including the compression engine. Let me jump to the next one. And I will now hand over to Rajkumar to go over the A-PHY.
Ariel, you gave a good overview of the program. And now I will take you through the A-PHY physical layer. So let's go to the next slide, please. So basically, A-PHY, we have developed two specifications, A-PHY 1.0, and then there is an enhancement to that, which we are calling A-PHY 1.1. And A-PHY as a physical layer is basically a full duplex, physical layer supporting power over A-PHY. So power delivery is supported, and bidirectional data is supported. Okay, and basically the A-PHY is directly connecting with the native protocol layers like CSI-2, DSI, and then DP, EDP, which is also adapted through protocol adaptation layer. So basically, these are the protocol layers. There are multiple protocol layers supported through protocol adaptation layer, and for the MIPI on protocols, it goes natively without anything. So this is the packet error rate of A-PHY is 10 to the power minus 19. This is taking into account the retransmission concept, and then it is supporting both bridge and not bridge solutions, wherein in the beginning, while we are adapting A-PHY into the applications, the bridge solutions will appear, wherein bridge to bridge is carried out by A-PHY, and bridge to sensor can be C-PHY or D-PHY. And over the evolution, these bridges will get eliminated, and natively in the sensors, A-PHY will directly get integrated. The channels supported are both coaxial and differential channels, and the length of the channel is 15 meter, 4 inline connectors, wherein you get 4 connectors. So the different section of channels are taken into account as per the vehicle harness needs, and it supports power over cable. Power is supported, and then this is supporting functional safety ISO 26262, And by the way, A-PHY is already adopted by IEEE in 2977-2021 standard. So you can even download A-PHY specification from IEEE also. So this is all a very big overview, a very top level overview of A-PHY 1.0. In terms of data rate, A-PHY is actually supporting 5 gears, gear 1, 2, 3, 4, 5. And by the way, gear 1 and 2 are NRZ, gear 3, 4, 5 are PAM modulation supported gears, which is PAM 4, 8, and 16. Data rates are given here, and the max supported data rate is 16 gigabits per second. By the way, it is PAM 4, then you can say 4 gigabaud. And Nyquist frequency will come to 2 gigahertz. So basically, uh, because of PAM modulation, your bandwidth requirement of the channel is very low. So you can use low cost channels, which is also one of the benefit of higher PAM modulations. With the uplink, data rates we have initially in 1.0 it is 100 Mbps, but in 1.1 it is increased and it is 120. I don't read. It's I think 100 200 Mbps in the A-PHY 1.0 1.1, sorry. In A-PHY 1.1, additional enhancement over 1.0 are: number one, we are supporting low PAM modulation in lower gears so that you can use low cost cables, which is basically some vehicles are requiring that kind of applications. Uh, Uplink data rate is increased from 100 to 200 Mbps. Support for quad star cable is provided, so dual differential lane are supported in A-PHY 1.1. And if you use uh, both the differential lanes for downlink, then you effectively increase your data rate from 16 gigabit per second to 32 gigabit per second. And basically, the additional configurations are here. One option is both lanes are used in dual downlink configuration. You get 32 gigabit per second effectively. Other configuration is reverse downlink, wherein the downlink primary downlink is 16 gigabit, but reverse downlink supported is 4 gigabits maximum. Okay, so this is one configuration, which is basically asymmetric configuration. Then you have got a fully symmetric, wherein uplink and downlink, maybe I will say, I will not call it uplink, maybe it's basically both directions are equally carrying the equal data rates of 16 gigabit per second maximum. So this is all A-PHY 1.0 and A-PHY 1.1, basic overview. So if you really look at why A-PHY is so robust and efficient, so basically the beauty of A-PHY is that it is supporting local retransmission mechanism. So retransmission means if there is a packet failure, receiver or maybe sync can request through the uplink channel to retransmit the packet. So that means any lost packet can be requested for retransmission. And this is, and when you do the retransmission, you can actually, generally the constellation is also reduced. So your SNR improves. So basically, this is the scheme which is making A-PHY very robust. Okay. And other approach is that A-PHY receiver has got a NBIC, narrowband interference cancellation. So wherein if there is a noise which is attacking the link transceiver, and when it reaches the receiver, and receiver might fail. So there is a mechanism of retraining my receiver, identifying the noise signature of the attack signal, and then rejecting that spectrum of noise and recovering the link. So this is basically NBIC, which will come in the next slide. But overall, that is a top level mechanism. So basically, retransmission has got two approaches, wherein within 6 microsecond, if there is a packet failure, you can request it and then it will be retransmitted again. So there's a time bound retransmission mechanism. This retransmission mechanism is local event. It is not visible to upper layers. Okay, so upper layer is not involved any management of retransmission. It is lower layer um, affair which is handled. And then within a single hop, my sync can request a source to retransmit a specific packet. Okay, and while retransmission is happening, the modulation is also dynamically played with, wherein um, you can have a higher resilience, and then maybe you can ask for a lower constellation packet transmission. So highly resilient overcomes large thousands of symbol error burst, and then beauty is that there is a buffer on the source side. So whenever the data is received, it is buffered, and every packet is having a counter, message counter, and so you keep track of every packet transmission through its message counter. You can request a packet if there is a failure of any message through its message counter you can detect. And then so basically, it's like you are keeping track of your packets which are coming from your upper layer. They are given MCW and then they are transmitted. Then you receive the acknowledgement if the packet has been received at the sync side. Okay, so it's like dynamically managing your data traffic. Modulation means tens of millivolts of noise can be rejected by the digital signal processors at the receiver, and the basic building blocks of source and sink are here. Like PMD is a physical media dependent, PCS physical coding layer, retransmission link layer, adaptation layer, protocol layer. This goes through a channel and then you repeat it on the sync side. So this is a overall a very basic top level block diagram. And here the overhead is less than 10%, so 90% is my throughput, ideal data throughput. And this is the overall, I think I can speak on this slide. So let's go to the next. So here basically the system simulations are presented here, wherein we are trying to share how the receiver will reject the noise, which is just in time cancellation, and recover the data transmission. So maybe if you look at on the left side, so this is my transmitted PAMs and this is my received, and at this time you get an attack. And when you get an attack, your receiver really is not able to detect your symbols because of this noise, and you basically your trans receiver, your basically data communication is not happening at that moment of time. Okay, at that moment of time, whenever there is a failure detection at the receiver will request the GITC, which is just in time cancellation training pattern, coming in from your source to sync, wherein the pattern is known to sync, and then the digital signal processing block on your receiver will detect the noise signature because it knows the packet symbols which are expected. Then it will calculate the error, and from the error it will calculate the taps FFE DFE, and basically which will get automatically aligned to a specific noise signature, which is basically the attacking noise, and you recover. And when you are recovering, you are going from constellation say 4 to 2. This is now, and then you remain in that time till your retraining is done, and then
Right.
you revert back to your original constellation.
As Raj mentioned, this is the current A-PHY capabilities and overview, and I will try to cover in the time that we have left our plans of the A-PHY working group for the next generation of A-PHY. So what's the next A-PHY? With the generic name at this point, A-PHY 2.0. So when we started looking at the next generation, the goals were defined as support of the next and emerging architecture and use cases, and specifically the zonal architecture and a software-defined vehicles needs. In addition, the modern automotive cockpits and the involvement of the large screens are taken into account. And of course, as usual in the MIPI specification, it was important for us to maintain the backward compatibility and maintain the be forward compatible and being able to continue and expand the capabilities without limiting it to a specific solution. We have focused on the PHY layers, so all the upper layers, the adaptation layers, as mentioned by Ariel and Raj, are not changed and can work seamlessly between the different generation of A-PHY. And of course, the trademark of A-PHY, we will maintain high MMC resilience and low packet error rate because unfortunately, the noise environment in the car is not going to change. So going forward, what we're looking at is doubling the downlink and reaching 32 gigabit per second over single lane, either coax or twisted pair, with and keeping the 90% net data rate for the application, meaning 28.8 gigabit per second for the application. The uplink throughput also been increased, and this is much more bigger increase. It will be reached to 1.6 gigabit per second, allowing 1.166 gigabit per second data rate that allows the A-PHY network to support 1 gig Ethernet in addition to the high-speed data link, downlink, and of course, any adaptation or enhancements to the current Ethernet adaptation layer that is supported by A-PHY will be added as part of the PAL development. Of course, we continue in parallel to enhance the type of interfaces that are supported by A-PHY. Depending on request from members, we add every time, almost every quarter, we are adding more interfaces and supporting more interfaces. On the right, there is just one more smaller update. There is an A-PHY 1.1.1. This is mainly part of overall MIPI Alliance to remove any offending terminology. So there is update to have inclusive terminology in that spec, and also any errata that was approved for the A-PHY 1.1 was also included into the spec. We are working on a test program at a reference compliance test suite to be completed next year, and we are running a pilot compliance program inside the working group in order to provide it and be able to go to the next level with that. From liaison and cooperation with other organizations. So as IEEE already adopted the A-PHY 1.0, we are on a path to be adopted also the 1.1.1 by the IEEE. And in the resource capabilities, so we have added a retraining and retransmission up node. There is a power over A-PHY up node, and we are planning to have a power over A-PHY specification that will enhance the capabilities of supporting remote power devices with different use cases. So, as said, the the A-PHY 2.0, so the downlink gear now will be updated with 2 more gears that tentatively are now called gear 6 and gear 7 to run PAM 8 and PAM 16 up to 32 gigabit per second. And there is also under discussion adding capability to support an optional capability to support gear 5, which is a 16 gigabit per second with a PAM 4 under certain conditions. From the uplink perspective, so we will maintain, in order to support similar implementation, we will maintain in the new uplink gear the same modulation scheme, but run it in a higher speed, higher frequency, so we can reach the 1600 megabit per second with the net data rate of 1166 megabit per second. So for zonal architecture, so this is becoming more and more popular and being the guideline for many of the designs. And in general, you have a lot of sensor being aggregated as a zonal ECU or zonal unit, then being transferred into the main computing unit. So most of these sensors are asymmetric data with most of them are that need control are at a lower bandwidth with sensors like radar or camera or LiDAR that might require higher bandwidth. So the nature of A-PHY being highly asymmetric is well suited to a situation when you have aggregation of multiple devices with no or very little processing capabilities, keeping these devices at the zone aggregator to be simple and pass the data to the main CPU. So from that perspective, A-PHY is a very good match. And this is how we are trying to convey that with, and this is just an example for one use case of being able to implement A-PHY-based zonal architecture. And of course, this is just focusing on the front side in order to reduce the clutter in the slide. But you can see that each zone ECU aggregates multiple sensors and actuators. It's a very high speed in direction of the central computing unit with the camera, radar, and LiDAR. And you can run a bidirectional information up to 1 gigabit per second, and even, let's say, 1 gigabit Ethernet, and even more control interfaces in addition, like SPI or I2C or I3C, to support this kind of solution. And it doesn't matter if you have a direct connection or from a sensor or camera or through this aggregator. This is actually doing everything in the native protocol like the CSI or DSI, and with very little processing needed at the end units. So this is, as mentioned, this is a solution that for certain use cases enables to simplify the zonal ECU. This is it requires a low computing overhead. It has lower protocol overhead because we maintain the native CSI protocol or Ethernet. It is designed to have ultra low packet error rate, as mentioned by Raj, 10 by minus 19, in a very high noise environment. And it's maintaining the future looking. It will enable you to go forward because it's a scalable downlink speed from 2 gigabit up to 64 gigabit at this stage, and then even further when we go to the future. It's flexible. It has rich protocol support, and as Dariel mentioned, the security. It's supporting a layered security scheme, and as part of the A-PHY, it has the embedded functional safety in the A-PHY and also at the protocol level, like in the Ariel showed earlier today. And of course, it always, as most of all of MIPI protocols and PHYs, it guarantees interoperability and backward and forward compatibility. Next thing is that we are going to enhance for A-PHY is the power over A-PHY. Our current capabilities are defined in the A-PHY specification, and the plan is to separate the power over A-PHY to an independent spec and enable more types that will enable higher power to support newer use cases. So to summary, and I hope we'll have time for Q&A, the A-PHY provides a resilient and robust automotive SerDes standardized solution for camera, sensors, and display application. The MAS is providing end-to-end functional safety and security protections and flexible in-vehicle network topologies. The A-PHY can support all the different topologies that are needed for vehicle architecture, electronic architecture. It has native support for standard protocols in MIPI and outside of MIPI, like VESA. And the camera service extension and the display service extension are already including end-to-end functional safety services, and the next generation planned in the near future will support also the security as described by Ariel. And we expect the A-PHY and the MAS to continue the scaling and continue the advancements in order to support the evolving needs of the automotive market. So again, these are resources that can be shared, and I think that this brings us to the end of this presentation.
Yeah, thanks, Ido, and thanks, Raj, Ariel. We actually have a lot of questions. Unfortunately, we're really short on time, but maybe Ariel, if you can join us quickly. There was a question. Maybe we can try to answer in 45 seconds or so. Is compression done after the protection? So does that mean the compression has to be lossless?
So let me take it. So the compression is lossy. But the compression engine mandate on the transmitter side to generate the reconstructed pixel in the feedback loop of the compression engine. And in that way, we're able to have exactly the same CRC matching on the TX side, which is calculated on the reconstructed pixel, as well as on the RX side, which is doing the decompression and making the reconstructed pixel.
Cool. Right. Thank you. Yeah, sorry to rush everyone, but man, a lot of really interesting things going on. We will definitely answer all questions by email that was sent into the chat. So thank you. We are out of time. We do have a short break before the next session, but I just wanted to thank our speakers again. Thanks again, Ido, Ariel, and Raj.